So great. So this is the workshop. This is our platform where you can do some cool physics. So if you've never used Aleph before, it's slightly different in terms of setting up your programming workflow. So the main idea is that in a normal programming language, what you would do is you would maybe go online, you would look at like people use VS Code, or if it's a compiled language, you'd find a compiler and you would learn how to kind of assemble your code. So just to be very clear, this is our browser. It's a browser platform where you can run Aleph code, but it doesn't necessarily run on the browser. So what we do is we have something called a compute agent, not to be mistaken with an AI agent. It's just something, a piece of software that helps you execute code. And it helps you install it as well, so you don't have to do anything. You just kind of run some simple commands. And from there, you can just go ahead and execute code on different platforms from one single place. So to get started, so just to situate ourselves in the platform, we have kind of a bunch of little things. We have a quick tour made by Jonathan where you can access all this. But actually, before I continue, at any point, if I say something that's not clear, if you're on the platform yourself, you can go check out our docs. So it's in the top right-hand corner. And we have a bunch of things here. So I'll reference the docs when I can. There's a couple of key sections. Namely, if you're super new to Aleph, the Aleph 101 page is probably the best place to start. You could follow along throughout the presentation, and I'm going to go through some examples here as well in just a few moments. But it kind of runs over the basic bones of Aleph that you need to just start coding. Then we also have the Learning Center. The Learning Center is if you know a little bit of Aleph, or this isn't your first session, but you want to get started on more serious things, what you can do is you could look at the concepts and the tutorials. So we have a quick start for helping you kind of starting to code, which I will do with you guys. But the concepts here really go over some more pedagogical aspects of the language, kind of our philosophy, how you should code, all these things. So for example, from any body, we have, say, fermionic operators. We go over their algebra. We show a little bit of code, how you would call them, so on and so forth. We go over, say, non-interacting fermions as well. We have some examples. We're very explicit with these. So this is kind of like, okay, maybe you're not an expert, you're learning to work on a project, you want to access these, you'd go to the concepts. And so plotting, for example, is also here where we talk about these things. Then we have tutorials. These are a bit more cookbooky. These are like, if you're going to work on something, just pick a category and go. So for example, if I want to work with, let's say, solving the XY model in 1D with DMRG, I would just go ahead and follow this. We have some code. It's not super annotated because it's meant to be more like, let's go fast. And then you could frequent, say, tensor concepts if you have any questions just above here. And then lastly, the most diehard intense option is the library reference. This has explicit programming documentation. I don't know how you guys are. I like looking through documentation sometimes. So suppose I have questions about the quantum toolkit, which we'll be going over today. Maybe I want to look at the create operator or Coulomb sum. This will be a bit more explicit with parameters and so on and so forth. So at any point, frequenting the docs is a good idea. So that's the docs. Now, as the overview for the whole workshop, we have a couple key things. Here at the bottom, we have our output panel. You can drag it and move it around. This will be useful for displaying our output. We have Kai here, where this is our AI chat agent, where we'll go through some examples here, and it can go away. And then on the left-hand side, we kind of have the main work pieces. So on the left-hand panel, I've collapsed mine. We have we have a file explorer where you can create files, folders, upload things, things of that nature. We have a search as well. You could search within your files. Fuzzy search is kind of useful for organizing yourself. Then we have jobs. This is one of our compute modes, which I'll get to in a second. So if you want to schedule a job like you would a cluster, this is how you would run it. And we have our agents. So speaking of agents, like I mentioned before, our compute system relies on these agents. All this, what this really means is we install it for you and we help mediate version updating and all these things for you. So we're going to go ahead and install our first agent. You guys should see, if you guys open the tutorial.aleph file, there's an option at the right-hand side up top here that has the interactive or a shared agent. You can use this as well for the purpose of the tutorial. but for installing an agent, it's fairly simple. So we're going to install a personal agent. This is one that you own in a sense of you have access to the computer directly. So I have my laptop, for example, but I have also these two registered personal agents called KPU and KPU2. These are our company computers. So these are physical devices I have access to, so I can install an agent no problem. If you have a cluster somewhere else, you may or may not have access to, you need to ask for permissions. Here we also have cloud agents. Not all these are available to you guys, but the interactive one is. And so this is some compute cloud somewhere that has some CPUs that we can harness directly, but we won't be focusing on those today. So okay, so first thing I want to do is I want to add an agent. I want it to be able to run code. So we're going to go create an agent. I'll call this laptop because I'm going to install this on my laptop. We're going to create this. Okay, now we get this thing. This is when you need Docker. I'm running a Linux distribution, so I have access to my terminal, which means that I don't necessarily need to go a little bit in a roundabout way. If you have a Mac, you can follow along very simply. If you're on Windows, the best way is to install Docker Desktop, which is very simple. You can install it fairly easily. It sets up Docker, and then it'll install an application for you. From this application, you can do exactly what I'm going to do. You're just going to find the Docker terminal, or just any terminal of any kind, within the Docker application, and we're just going to copy this output. So if you're on Mac or on Linux, I'm just going to open a terminal here. I'm going to paste the command into my terminal. It's going to have a Docker command, and it's going to execute. Basically, it's just going to allow the platform to connect to your computer or to the resource that you're using. So it's waiting. The second this turns green, we'll be able to move along. It just takes a couple seconds to get everything set up. Okay, it just turned green. Great. Agent is online, means I can run code, which is good. So this is the same setup for any resource that you have access to. So a desktop, or if your research group has some compute, you could just plug it in from there. Okay, so now I have the laptop personal agent set up. I'm good to run code now. So I'm going to go ahead and open the tutorial.aleph file. This is a file that everyone should have just booted up on your workspace, and you should be able to run through everything you need to from there. Okay, so we'll get started with this. So first, I'll start off with just some basic programming stuff about Aleph, just to make sure that we're all on the same page. Aleph is a currently scripted language, meaning it reads top down, it's interpreted. So you write a couple lines, it goes top to bottom, and it executes things as you need. Unlike Python or Julia, this is strongly typed. This is weakly strongly typed in the sense that there is no general things aren't polymorphic objects. So for example, a string here, or a bool, or a integer, they have a concrete type. So they're a thing I can't reassign to this afterwards. So in Aleph, we have 5 primitive types. So we have strings, booleans, integers, real, and complexes. And before I forget, in Aleph 101, you can see we have a whole thing about numbers and conversions to make sure your precision is good. Feel free to look at that. I won't get into that today, but it's very useful when doing precision numerics. From there, so we have our 5 types, but the second that these variables are created, they become the type that they're assigned to. So this a string will always forever be a string. It'll throw an error if I try to assign, say, a boolean to a string. And you can see here, you could uncomment these out. Comments, just by the way, are made with, you can do a block comment like this, or you can just have 2 comments for a line comment like this. So in Python, I believe it's just the hashtag. Hold on, my dog is being a bit ridiculous. Mustang, stop. Okay. So you can also put in semicolons. This is some nice stuff if you like. It doesn't suppress output, but it just separates lines. Everything can be printed, so we can print here as well. And you can also retrieve the type name just to make sure that things are very clear. And this is very useful in debugging because it gets quite useful to look at the types, especially when things are changing as you go along. There's no garbage collection, so every variable that you create lives forever, essentially until you specifically do something with it that would kill it. We'll talk about globals. yeah, there's just, yeah, there's some edge case stuff. We won't talk about this. You can also convert between the types when it makes sense. So you could just cast it really nicely like so, and you could retrieve the types that you would need. And it follows the similar integer arithmetic of promotion and demotion, no demotion, just promotion as we need. And there's rounding errors. There's rounding that occurs if you cast an integer. Okay, the most important things, control flow logic. So effectively, our if statements look like this. We use curly braces. There's no indenting like in Python. I personally dislike the white space indenting. It's very frustrating. But here we use curly braces, and they're a bit more like C++ style, C style if else. Yeah, so if, else if, and else's, and you should be fine. We also have switch statements for integral types. This is a bit more, this is not familiar in scripting languages, or at least not super used, where this is kind of like a jump table. It just looks at what the value is and it just goes to which case rather than going through the ifs. Okay, we also have for loops, of course. Our for loops are a little bit different than what you would expect. These are closer to C++ style for loops as well. So you just need to have, you declare the variable that you're going to for loop over. J, you have to assign it something. You give it a terminal condition, and then you give it how it should increment, for example. So here it increments by 1. The plus means make j bigger by 1, but you can also do j plus equals by 2 or 3, and you could stride it that way. Yes, you can print the summation here. Strings can be concatenated, so we have string logic as well. So you can just add things very nicely. This is nice for formatting. I won't go too much into detail about strings, but it's very nice. The single most important container that we have is the list, because you can for loop over it. That's the nicest thing. But lists are heterogeneous containers, so they can contain anything effectively, any type, which makes them nice for general purpose programming. But maybe for performance intensive things, you'd want to use an array or something that has a fixed length and that has only a single type to make things a bit faster, and so you're not guessing what the list does. So this is my list, for example, here, and you could add things to the back of the list by using pushback. You can use, when applicable, you can sort, reverse, extend lists. You can do all these nice kind of things. You can look at all this. You could see all of this in Aleph 101 in our docs. We have nice breakdowns about all of this. And then like I was saying, the most important thing really is what you want to do is you want to. Sometimes it's nice to for loop over a list. This actually will just make the ranged version of a for loop, which is a lot more easier to look at. You can also, if this was just a list, for example, like if this was just a list and list was defined previously, then this would be much easier to for loop over. We also have over here as well that the last element here is not included. So when I have this notation with the 2 dots, it means this effectively. Okay, you can also stride. Yeah, you can also stride the list. So this will jump grab every second element in the list. Okay, I'm gonna stop here for Aleph specific code. It's fairly intuitive, but it becomes a lot easier once you use it a handful of times, and hopefully we'll get a bit more accustomed to it through quantum examples. Last thing. Functions, other most important thing. So if you define a function, you just have def, and then you give the function name and then the arguments. If you want to leave this type open to whatever the argument should be, you don't have to provide any type info like you would in Python, and you can get this nice little print here. But if you do want to add type info, which is useful when you're sharing code with someone, this will actually introduce a guard, which is basically, if you try to run this function with something that's not an integer, it'll be like, hey, you expect an integer, it's not an integer, and then it throws. So you can be rather strict. You can also make lambdas, for those of you who like using lambdas. And you can also, functions themselves are first-class citizens, or in Aleph, meaning they have their own kind of identity. They're not just something that you could that you just make that take in other objects, so they are objects themselves. So you could pass functions as well. Okay, I'll stop here. Yeah, and we also have a timer, which is nice for benchmarking. Okay, so that's Aleph 101, speed ran. And actually, I should make a point here. I haven't ran this yet. So I'm going to actually, I want to run this script. So what I'm going to do is I'm going to select the laptop, which is the agent I just installed, or you could use the interactive one for now, it should be fine. And then I'm going to do plus here. And so at first, your first ever execution will will take a little bit of second to download the newest runtime. This takes care of versioning for you. This happens every time we push an update. Today was one of our update days, so I'd have to do an update. And it's going through. And okay, we're a little slow today. So the duration here should be a bit longer. But okay, so we printed a bunch of stuff, and this prints the output of other stuff that we care about. Okay, now for physics. Now for the fun stuff. Optimization. Okay, so one bread and butter operation, or one bread and butter, some functionality that we have is exact diagonalization and quantum operator support. So we allow you to express Hamiltonians in terms of operators. You can manipulate them. You can act them on vectors. You could do all these little things. Cast them to matrix product operators, have circuits, and it's very cool. So yeah, so I won't go into qubits and f-bits, but effectively, actually no, I will. Very quickly, product state of spin 1/2 particles called a qubit. This is just useful because we can act with operators onto things. So here, this x is the Pauli x operator acting on site 0. We 0 index in Aleph, and it acts onto the product state, and it does this in place with this operator here. And it could also do it out of place by using the star, so you multiply into it in both ways. In place means it doesn't make a copy, it just takes the object, changes it, and then you can use that object again. Whereas the out of place with the star means that you act on it on, say, A, in this case, this very specific line. You would act on A, and then you would modify a copy. So you would return a new object. A would be left untouched, and C is your desired output. This is useful in many cases as well. Here, S plus and S minus are the quantum operators we support. So instead of just kind of enumerating all of them, if you go to concepts in our learning center, you go to many body and spin 1/2 operators. You can see we have some things here. Identity X, and it kind of says you what the mathematical form, it tells you what the mathematical form of this is. We have projectors, Hadamard gates, if you're more into quantum computing. We have some fused kernels as well, all these things. These are great. We love operators. We love spin 1/2 here. Now, one thing I want to note here very quickly before I continue is that these are symbolic. So these operators here are not matrices. These are the quantum operators. So like they live in a Hilbert space, and they act as you would expect when they don't commute. They have certain Pauli relations, all these things. These are symbolic operators. These are not matrices. You could make them into a matrix by using the matrix factory effectively. So okay. And here we have some parameterized operators. These are kind of like our symbolic ones, except that maybe they have a parameter that they depend on, like a rotation or something. So we have operators that have a parameter, like a rotation x here, y, z. We have all these ones, different forms. And then we have matrix operators, which are like potentially if you have a very specific operator combination that you care about, you can use it as a dense operator as well, or a sparse matrix operator, so on and so forth. So tons of operators for you to explore. So here what we're going to be doing is we're going to be using operators to construct Hamiltonians, and then or circuits or the system that we care about, and then we're going to study that. So okay, we also have fermionic operators. We have create, destroy, for example. Okay, these operators can act on vectors. So if I make a vector of some given size, I could have my operator symbolically act upon my vector, which is a real vector. It has entries and everything like that. Okay. An operator, though, in general, will come in a product. It'll come multiplied with something or with a string of other things associated with it, like an operator product. So we have our operator framework, in order to be fully symbolic, has kind of full algebra control. So you have products and sums. A sum is a product of operators. A product of operators is the multiplication of operators together. So here at line 752, what we've done is we create this operator product, which is different than just an operator. It contains operators. So you can think of this empty product. So I've created an operator product object. You can ask the type name here if you'd like. And this creates the identity in some sense because it has no products. If I act on an empty product, which is just one effectively, it does nothing. So we can multiply things into it, like for example, the Pauli X matrix, or operator I should say, at site 0. And we could also multiply other things into it as well. We could very similarly make an operator sum. By default, operator sums are products of sums of products, and by having it this way, you need to specify what kind of coefficients you have for your product. So if you have a real operator sum, all the coefficients are real. A complex operator sum has complex coefficients. In this case, when you create an empty sum, if I didn't specify the as complex specifier here, this would default to being complex. Aleph is a complex first kind of language. This is all about the most quantum mechanical thing. Think about it's matrices, representations, complex algebra first. So we have operator sum like so, as complex. You could make this as real instead. So that should be sufficient. So if you wanted to do a real sum, which you could, this would be fine, except this would throw an error when you would pass in complex numbers right there. And just, I should mention that our complex numbers are prefixed like you would just add an I to the end of a number like this. So it's a bit more easy to read. I'll leave this as complex for the moment. And then you could print products, you can print sums. Now, great, cool. You can ask, Seb, why do I care about products and sums of operators? Well, you can simplify them. So you can perform operations on these operators. So what you can do, you can create terms for your sums. So for example here, this defaults to just an operator type. I should be very explicit here. When you perform a multiplication and addition of operators, it in general returns an operator, which is just like the class, the operator. If you wanted to specifically cast it to a sum, you would need to pass it to operator sum. It's a bit tedious, but the idea is that this actually keeps things very strict so that you actually have full control over what you're doing, rather than just kind of guessing as you're multiplying things together. You're like, okay, well, eventually this will be this is a sum, this is a product, and it's not clear, and there's some ambiguity there. So this keeps the lines defined. So suppose I have two terms, a product plus xy plus z, and I have x2 plus y2. I could put this into a operator sum in this form. So here, what I've done is I've taken term 1 and term 2, which contains sums. So these are two sums, and I multiply them together. So this will be some spaghetti. And then, okay, I'll throw in another term here, and I'll add in some, like a term with a very small coefficient in front, and I'll call this an operator sum. And again, because I didn't specify the type here as the second argument as real or as complex, it will just default to complex. If you tried to do as real, it would work in this case, but if I had a complex coefficient, it would not work and you'd get an error. So first, what I can do is I can flatten the nested structure. What this does is it just takes your sum, and then it expands everything. So it'll look at all the terms and be like, can I expand effectively? Then, now that I've done this, I can merge like terms. So as I flatten, it is possible that I get terms that are the same. So I would actually want to add those two terms the same. That's what our brain does. And then lastly, I can actually truncate the sum if I want as well, which we call pruning. And we're going to give it a custom tolerance of 1e to the minus 10. And so it'll kill this term at the end. And effectively, this does the basic algebra for us. And now we have a further simplification, which is specific to just Pauli operators for the moment. We're going to be adding other operators to this as well. We can use the simplify Pauli's function, which this just effectively performs on operators that have the same that act on the same site. This would just merge them together, and it would apply the Pauli algebra rules, which is very convenient, as some people here are working with already. Okay. So those are operators. That's kind of the gist about the symbolic uses. Now we're going to go into a partial symbolic / computational workload, and then we're going to go into the more computational workload. So like I keep mentioning, these operators are kind of just objects that you can use to do things. And so like to perform algebraic manipulations. And so in this case, what we're going to do here is we're actually going to check if an operator commutes with Hamiltonian, i.e. is it a symmetry of this operator. So again, like we start with all of our quantum workflows, we create an operator. Here we'll call it the Hamiltonian H. We're going to make an operator sum, and we'll just explicitly label that it is complex. Then here I put n to 4, but n can be whatever you want. In this case, here you can go rather large to over 36 sites if you want, since this is just a symbolic workload. Then what we're going to do, we're going to perform a for loop, and we're just going to inline some stuff to make it nice. And we're going to add to our Hamiltonian a ZZ interaction. So for the icing model, this is just our good old ZZ nearest neighbor in a 1D chain interaction, and we'll make it periodic. Why not? And then we're going to go here in our second one, and we're just going to add an on-site transverse field scaled by h. Here I put h to 0. You don't need to. This is the way it is. You can prune, so this will get rid of these terms here, and then you can print the Hamiltonian. So I already ran this code, so I don't need to run it twice, but effectively it should print it right here, like so. And so we'll keep it like this. So the printing, actually, I should mention, the printing here will print effectively, it'll tell you what sites the operators act on. It looks a little bit clunky sometimes. So if you have many, many terms, it's best to just index the sum and then just print term by term, at least in a column rather than in a row. But more or less should be clear. Okay, so what symmetries does the icing model have? The one that I know off the top of my head is the spin flip symmetry, which is just the product of x operators on every site. So basically we will make this operator, this Z2 symmetry operator. I'll call this operator sim, and I'll make an operator product. Again, an empty operator product doesn't have a coefficient, it's just the identity. And I'm going to multiply things into it like you would anyways. So you write multiply the x operator, and we ask the question, do they commute? Well, we have a nice handy dandy commutator function. It does the commutator for you. It does some shortcuts to make sure that's a bit faster. And we're going to just turn this into an operator sum to be very explicit. We're then going to flatten it. So here, this is another way to inline. Sometimes the flattened function will change the type depending on how coefficients are expanded. And so we need to be careful. But this is one workaround. And so you would just do my object equals a flattened version of my original object, and it'll just overwrite it. Then I will simplify my Pauli's, and then I will print C. So if this commutes with my Hamiltonian, I can conclude that the operator that commutes is a symmetry of my Hamiltonian, and it should be 0. So if it commutes, the commutator is 0. If it's non-zero, it doesn't commute. It's not a symmetry. So here, the line right after that I printed the operator, it prints the empty operator sum, which is just 0. So we confirm that Z2 symmetry has the transverse field icing model has Z2 symmetry confirmed in 2026. Okay, so now we're going to take another step further, and we're actually going to perform time evolution symbolically. So I promise this will get to doing some more heavier numerics, but this is what we're going to do, is we're going to evolve, we're going to do time evolution for an observable of our choice, but we're going to do it in the Heisenberg picture. So rather than getting time evolving our states in the Schrodinger picture, we'll just evolve the operator and then take an expectation value if we so please. So let me just uncomment this out, like so, with control here. And I'm going to run you through this. So effectively what we have the Hamiltonian parameters. We'll just pick these parameters because they're nice. Then we're going to pick some time evolution parameters. We'll do 4 time steps with a time step size of 0.1 and a cutoff of 10 to the minus 3. Now again, we rebuild our Hamiltonian like so. We're experts at this point, but we'll leave it in open boundary conditions. And we will set up our initial operator. So it's a bit important that we make our initial operator an operator sum, because sums have coefficients and we want to track this as well. A general, just an operator on its own is not a sum, it's not a product, it's just a pure operator. Products are, operator products are products of operators, and sums are sums of products of operators. Very, very wordy. Apologize on that. Okay, so now we begin the time evolution loop. So what are we going to do? We're going to do the Euler update. So this is a very simple example here. So if I do time evolution, effectively what we're solving is the Heisenberg equations of motion, like so, and we can actually take care of the of this ODE fairly easily. You can just approximate this like so. So we'd say that a t at the next time step is a of t at the current time step plus our small time step delta t, and the commutator of the Hamiltonian with our current operator. This is actually like fairly straightforward. It's not super stable for large step sizes, but for small step sizes, this suffices. There are more advanced methods you can use, like the RK4, which you can see further down here. Okay, I lost it. It's somewhere here. Yeah, the RK4. So you can have an RK4 helper here. So you can do RK4, which is just a different approximation to what we're going to do, where these K1, K2, K3, K4s are just other combinations of the commutator that are efficient. Okay, so what does the time evolution loop look like? So we're going to we'll take for our current step, which we only have 4 of these, so we have 0 to 3 in this list. We then take our right-hand side, so we took this as an empty sum, and we're going to take the commutator of our matrix of our operator, our Hamiltonian with a old, and this will be our first right-hand side. We'll flatten it, we'll simplify it in case we need to, and then we'll actually do the Euler update. So the Euler update will just be the previous plus the time step times the commutator, which is exactly what we calculated up here, and we'll put this back into a old because this is what we're going to keep calculating. And then we simplify Pauli's. Now, the simplify Pauli's function as well, you can pass your tolerance to it. So at the same time as you simplify, you could also prune the terms. So it's going to be the case that once you recombine terms, you'll actually get some copies of the same operator, and it just kind of does it for you. It's fairly efficient. And then we're going to print this. So if I run this, we'll see here after our first time step, we have y and z. And then as we go along, we have, whoops, there's more stuff printing. As we keep going, we'll see that we actually have our coefficients. We start to get the spread of the operators. So now over time, things don't necessarily commute, and so we get some non-trivial dynamics, and you can actually look at the Pauli's directly. So here you see that many, you have this many terms. They're not all the same weight, of course, but as you keep going, effectively, you'd get to the boundaries, and you get some equilibrium stuff, which is rather cool. Okay, great. So that's symbolic time evolution. Very nifty. Just for the sake of clarity, I will comment this out again. Okay. Now, ED. Who doesn't love ED? I love ED. ED is great. So now that we've beaten the other facets of the Ising model to death, let's beat some more. So what we're going to do is we're going to do some ground state analysis. So what we want to do is we want to take the we want to obtain the ground state of this model. So very simple. Again, we're pros, guys. We're going to make the Ising model again with our operator sum, but we can make it real because the operators z and x don't involve complex numbers. So we get a little bit of a speed up by using real sums and real vectors. And so we're going to pass it to our iterative eigensolver. Very, very simple. We make our operator, and we pass it to the iterative eigensolver, and then we're pretty much done. So what we're going to do is we're going to pass the Hamiltonian, the dimension of the Hilbert space, the number of states that we want at the lower edge of the spectrum, and then we're going to pass it some options. So this is a type I haven't covered, but it's a map. Essentially, it associates to a key, in this case a string, some kind of value. It can be undetermined. So here it passes 2 booleans, and here it passes a Krylov dimension. The Krylov dimension is just a technique that controls the accuracy of the iterative eigensolver, but it does so at the cost of more memory. So the larger the Krylov dimension, the more memory it takes. But it's still memory efficient, but it's just something that you have to carry, and it's essentially copies of the state that it's going to activate, that it's going to act on. So not super focused on exactly the details of this, but I'm more than welcome. I welcome questions about this, and we can talk about it afterwards. But effectively, it gets the 3 lowest level states. Then this will return a list, effectively, of the eigenvalues and the eigenvectors, and we can retrieve them like so. So lists can be indexed like any other list you would in scripting languages. And then we can just print the eigenvalues in this case. So I know I've already run it once before, but we're going to go. This is fairly sizable. Okay, so 12 is huge in this case. So this is why it's taking it's taking too long. Hold on. Let's do 8. Even then, 6. So we'll do 6. So here I'm asking for the 3 lowest levels. This is for n equals 16. It should be a little bit faster than it is. I think we recently made changes to this, but that's okay. So it'll take a couple of seconds. I believe this is in serial. I think this is why. I think we just pushed this today. But, oh my goodness. Wow. Okay, so it returns here 2. Okay, that's a bit strange. It returns 2 of the values. Basically, we get things that are actually very close, and that's probably always taking a little bit of time. So these 2 states are degenerate. And yeah, cool. Now, suppose, okay, so now we have the state, you can extract it, and you could do expectation values, which is useful for a lot of quantum workflows. Next, now suppose we want to study the dynamics, but not in the operator picture, but in the state picture. We actually have something called Krylov time evolution, which allows you to do time evolution for larger system sizes using the same math that underpins the iterative eigensolvers. This is a bit more complicated, but what you do here is you go through, you get the number of sites, the Hilbert space dimension, all these things. Yeah, 16 is rather large here as well. The Krylov subspace dimension, all these little things, set up your model. And then you make a function, this x complex dtx, and this is a lambda. And effectively, what the operator function does is it approximates this function. And the argument to this function will be the Hamiltonian. So it basically approximates this, hence we would call it operator function, because it approximates a function of an operator. And then from here, you construct U, it's a unitary, and then you can act on, we pick a specific initial state, not too important for the moment, but we set up observables, in this case, ZZ, the 2-site ZZ operators, and what we're going to do is we're going to evolve our state here. I guess here it's not actually evolving. You would need to do this, like so, and take a little bit of time, but it'll evolve it, and that's that. As this runs, we also have DMRG. I won't get into this today. Okay, so that's the speed through of the tutorial. Now, suppose you want to take this information and you want to do something with it that isn't just follow along the tutorial. You may want to ask, I'll just end this because it's just going to be fine. It's okay. Now, suppose you want to do something that is actually non-trivial. So suppose you have a desire to let me open this here. Oop. Yes, thank you. Suppose you want to learn about like a different model. Suppose you want to do more ED, let's say, because you also agree with me that ED is the ultimate technique that runs the world. You want to actually do something different with a different model, and you want to crank the ED. So how do you do this? You open up Kai. Now, Kai is our AI tool for helping you just basically do work. It knows our docs. It helps you get started on projects. It helps you with a lot of things. It helps me with debugging sometimes, and it also, personally, going through the documentation at times is a bit difficult, not because it's not clear, but because there's just a lot to go through and you're not really going to sit through everything, go through all the types. So it's also useful to look up documentation, super useful to get coding. So suppose now I am like someone obsessed with ED, which is true, but also I also like to study different models and on different geometries. So suppose I care about the Heisenberg model. I have a kind of a prompt already set up for this, but basically I'm just going to describe it as it runs. So suppose I care about the antiferromagnetic Heisenberg model. I can ask Kai to create a markdown file for me with all the information that I need about the model. that needs to be checked, of course. It defines terms, gives me some phases, tells me where I should expect some physics, and maybe even what symmetries the model has. So we'll just submit this here. Kai can do many things. Kai can look at your open work. It has access to your files. It won't change them unless you actually ask, you actually enable file edits, but it can give you a diff. It can allow you to actually like create, like you can work on a file, be like, hey, what's wrong at line 293, so on and so forth. So as it keeps going out. It can also run code to check. So it's set off by default because suppose you give it like, you want to do DMRG for like 2,000 sites with like a bond dimension of 10,000. That would just nuke your computer. It would nuke whatever system you're working on, so you don't want it to run, of course. But it can do those things, and so I'll show you how we can use this. But this is kind of how I would start a project personally. I would start with first by writing, okay, I want to do this. Give me the information I need as the expert to start my project. This will give you some information. We've also enabled recently Kai to be able to access the archive and able to give you sensible references. We should still check them, of course. Here, yeah, it'll give you the Haldane physics, which we all love. Auerbach, interesting. But that's new. So here I have a markdown file. We have markdown support on the platform. So I'm gonna just say create new file, and I'm gonna write this as my notes, and I'll do create file. Okay, I'm just gonna put Kai off to the side now. A bunch of text has been written. We can make this more presentable and digestible by using the preview markdown button. Again, let me just move this over here. We can do preview markdown, and we can go here, and it'll find the Hamiltonian for us. It'll explain to me what D is. It'll explain to me what all the terms that's using, because it gets a bit confusing if by the end of it it's like, actually just tune this coupling, and then you can't really find it. It'll discuss some symmetries because I asked it to. It can give all these nice little things, information that may or may not be pertinent to you. I mean, that's what I asked for, and that's what I get. So suppose, okay, maybe this is overkill for me. I'm like, okay, let me get started in 1D. So first, I would actually like to maybe perform some one-dimensional ED on the Heisenberg model. So I have another one, and maybe I want to sweep through the phase diagram. Maybe I doubt the phases that Kai has spit out, so I want to check them for myself. Totally normal thing to do. So what I'm going to ask here in the follow-up prompt is I'm going to ask Kai to generate a script that gives me 10 points of the phase diagram for some range of values that are appropriate, and then I'm going to calculate the gap between the ground state and the first excited state. And then I'm going to ask Kai to plot actually this sweep, and I give it some info about plotting the y-axis and the x-axis names. And just before I forget, I know here I'm focused on Hamiltonians, but the circuit stuff is very similar. So if you're interested in circuits, whether you're interested in like quantum computing or just general dynamics of quantum circuits, the same goes for how to approach it, maybe not looking for eigenvalues, but you would just you would construct a circuit as a product of operators. So you would just make a layer on different sites, and then you would act on it. We have tutorials for this as this is running. If you go to docs, you would go to, we have a tutorial made by Jonathan on operators in dual unitary chaos. His is a bit more, this is a bit more complex, but I can also look at there's more than this. But effectively, you make an operator. Maybe it's flow K physics that you care about. So what you would do is you would act with, you would just make one operator product, and then you would act on this many times with the same operator, and you would get things. So here, operator diagonal. This is a bit more. No, is it the kicked one? I forget. Getting started, numerical methods, time evolution, Flokin quantum circuit models here. Yeah, so we can do it like this. Effectively, here it's a bit more sophisticated again, but the point is that you make a circuit like as an operator like this, and then you would, hello, sorry, I think I lost my camera there. You would make the operator, and then you would act on it. I just need the last line here. Yeah, you would literally just do this. So you make UF that you desire, and then you would act on it like so. Following this tutorial is good, and if you have any more questions, just ask the Discord. We're all Does that help? Okay, great. It did the thing I asked it to do. We're going to create a new file. We're going to call this 1D chain, as it says here. And then I'm just going to run this. Okay, so very quickly, you can supply arguments to the script. So if you're running many things or a phase arg, you might want to switch points at which you're doing things. You can do it. This is how you would do it with the get args. It's a bit more advanced for the purposes of this example, but it's kind of useful. And so when you go to run your code with the plus here, you'll actually get a prompt to say like, okay, I want this to be, I don't know, like 20 million or some crazy number. It also has a default value you can see back here as 10. So I'll just let it to run like so. And it'll go ahead and do this. And so here what it's doing, it's calculating the gap effectively between a bunch of points. And okay, it's done. It took 8 seconds. This is for n equals 10. Oh, sorry, no, this is not for n equals 10. This is for, yeah, this is for 10. So great, it's going to pop up into a figure file. We're just going to open the figure file, and boom, we get some stuff. So it picked a range. Of course, you have to check this. This is not just believe what you get out. You want to inspect that this is exactly what you would like to do, that the physics is what you expect. This is just a quick way to start getting into your work. And you can see that the gaps tends to be big, close to where the anisotropy is. You can consult the notes that Kai has generated for you. You can check the papers that you're working with. But you can see here that it shows you something nice here. I use a scatter plot. You can use a line plot, so on and so forth. Now this is great, but suppose again, I am super diehard for ED. What I would like to do next is I actually want to try more interesting, non-trivial geometries. So what's the next step that I could do? Well, I could ask, very simply, well, what if I was in 2D? Like this is 1D. 1D physics is known. I want to do new stuff. So very straightforwardly, let me ask what the model class is. So if we think about it, while this runs, because it'll take a little bit of time, when we construct our models as physicists, really what we're talking about is a geometry, so the lattice and a basis, interactions, and then observables about it. So we really have a whole system, or what we call at Kothar a model. And this model is the thing that is interesting. It's not like just the operator sometimes, just lattice, but in condensed matter, we care about all of the whole bundle as a whole. But if anyone has ever worked in any 2D system, it's very tedious to program. So the model class helps you kind of achieve any 2D geometry that you care about or that is possible. And it allows you to have a lot of control over it. You can do this with a code, like a code-based way, which for some people, like I personally quite like it. You have a lot of control, and then you create this model object. And then the model object is the thing that you can use to create operator sums, like the things that we've been seeing so far. Or if you're doing tensor network techniques, matrix product states. So it basically serves as an entry point to some more complicated physics, but in a way that you can palette. Now, I admit programming is not always fun, and so even if I like having hands-on control of the model class, it's a bit difficult. So what we can do is we can actually just ask Kai directly to kind of prepare a whole model for us to inspect visually, and then we could port it to code. So instead of having to go through coding, we can just ask Kai. And again, Kai is useful for getting things started and going. You as the expert will know exactly what you desire. So I have another prompt here where I'm just going to ask Kai to make a Heisenberg ladder for me of 10 by 2, so only 2 legs. And then I want to view it in the model editor. So what you can do, if you right-click on the file explorer, you can do new file, and you can have a lattice model. And I'll open this up in a second. But effectively, the lattice model opens up our model editor, and it creates kind of another environment where you can basically tune couplings and be very complicated with your geometry. But if you're not familiar with it, it's very easy to just ask Kai to do it, and Kai can render figures, can do a bunch of things for you, and will spit out this file. Now, strictly speaking, the data, like what a model file is basically a bunch of information about how the layout is formed. So here you see Kai writing this file, but this is not what you're going to see. This is just as it writes, and yada yada yada. Perfect. So it explains kind of what the couplings were. Oh, and a picture, even better. So okay, so let's create a new file. So you're always open to just open this. We're going to call this my model. And we're going to open this up. So, okay, thank you, Kai. So now I can drag this around and I can zoom in. And what I've effectively done is I've created a Heisenberg, let me close the file explorer for a second. I've created, or Kai has helped me in creating a Heisenberg ladder. So there's a Heisenberg interaction on every rung and ladder, but with a tunable rung and leg coefficient. So we see here we have J leg, J rung, J leg, J rung. I have personally studied a system very similar to this, so this is very nice to be able to do. This is comprised of 20, it's 10 by 2. Here I think it did it in 1D, but with a line it looks like, or with a lattice and a basis, which is fine. And so yeah, so great, this looks great. Seb, how do I use this? Valid question. If we go back up to the prompt, or to our chat, we can see, so it explains the lattice. So this did 10 by, it's not exactly what I wanted, but that's okay, this is still fittable. We have rung couplings, and it has different colors for everything, J rung and J leg. And it also comes with an observable. So very importantly, once you pick an ordering for your 2D system, what you want to do is you want to ensure that you can, you want to be able to actually measure things onto it. And so this will also ensure that the order, it's going to give you an object, and it'll give you an observable that has the correct ordering for you to do, because it's going to eventually have to collapse things into 1D, as with anything. So okay, so it defined it, and then this is how I could load it into Aleph. So let me just copy this. Let's go to the end of the 1D chain here. Let's see. Okay, interesting. So I'm going to put this in here. I'm just going to give this a little bit of a space. The file name, I think I called it my model. So we'll do this. And from here, I won't do the full workflow, but I could run this again. This should execute. Of course, it's going to run the code previously, but effectively what this will do, this will load in the model from this file. And then here, because I left the coefficient general, so if I look at J leg and J rung, what are we upset with? Quite file. Okay, it's a naming thing. I have to fix the name. But oh, it's this. So sorry. When I look at the names, I have J leg, J rung. These are, it's not a numerical value. You have to give it something. And so once I load in the file, I have to say, okay, my J leg and J rung are worth something. So the code executes, so we're fine. And then from here, you can do things like my model dot, I think it's opsum. I could, even better. Why don't we just look at the docs? So if I go to library reference, quantum toolkit, I'm going to look for a type because it's a concrete type. It is model model methods opsum to opsum. This is the observable to opsum. Add observable coefficients resolved. Okay, we ask Kai because we're confused. Say, how do I turn the model into an operator sum? And I think you just pass the model directly to the operator sum, if I'm correct. I can check this here. So model, this wouldn't be here, would it? Yeah, exactly. So you just pass it like this, which is very nice. And then you have your Hamiltonian, and then you can go and do stuff. Okay, that is our quick tutorial for today for getting started with Aleph, setting up your agent, a little bit of coding, introduction to the operator framework, which is symbolic, but can be used for numerical payloads. Here, I didn't talk about converting to matrix form. You absolutely can. You do matrix, and then your operator in here, and then it'll turn it into a matrix, and then you can work in this matrix form. Yeah, so just things that you need to be aware of. Right. So if there are, that's it for the